Hey everyone, and welcome to this explainer. I am absolutely thrilled you're here with us today because, well, we're going on a seriously fascinating journey. We are going to do something pretty magical, visualize the completely invisible. We're literally shrinking ourselves down to follow the journey of a single electron inside one of the most incredible scientific instruments ever built, the Scanning Electron Microscope, or SEM for short. If you've ever wondered how scientists capture those insanely detailed 3D images of a fly's eye or the tiny crystalline structures of metal, you are exactly in the right place.
But before we get into the actual machine, just think about this number for a second. Less than 1 nanometer. To put that crazy scale into perspective, a single strand of your hair is about 80,000 to 100,000 nanometers wide. Think about that. Today, we're exploring a piece of tech that resolves features smaller than 1 single nanometer. That mind-blowing resolution limit entirely rewrites how we understand the materials all around us.
So here's our quick roadmap for today. We'll start with a welcome to the nanoscale, explore the anatomy of the microscope, dive right into the interaction volume, cover prepping the perfect sample, see the invisible final results, and finish up with an SEM versus TEM showdown.
All right, Section 1. Welcome to the nanoscale.
Okay, let's dive right into this. To really appreciate what this microscope shows us, we need to make sure we're speaking the exact same language. First up, topography. You probably know this word for maps, right? Well, it means the exact same thing down at the microscopic level. Topography is all about the surface features of an object, literally how it looks and its actual physical texture. This is absolutely crucial because a material's surface texture directly dictates its everyday properties, like how much friction it has or how it interacts with liquids.
Next, we have morphology. Now, while topography is all about that outer texture, morphology zooms in on the specific shape and size of the individual particles actually making up the object. Think of it this way. Topography is the overall shape of a brick wall, but morphology, that's the shape and size of the individual bricks themselves. And there's a huge direct link between those individual building blocks and the overall strength and behavior of the material.
Finally, we've got composition. This is exactly what it sounds like, the actual elements and compounds that an object is made of, plus their relative amounts. So the big takeaway here is that an SEM doesn't just snap a pretty picture, you know? It's a powerhouse analytical tool that tells us about topography, morphology, and the fundamental chemical composition, all at the exact same time.
Moving on to Section 2, Anatomy of the Microscope.
So now that we know what we're looking for, where does our electron's journey actually start? Let's check out the physical machine. Starting way up at the top, we have the electron gun. This typically uses a tungsten filament to generate a beam of what we call primary electrons. These primary electrons get accelerated straight down a high vacuum tube using a massive jolt of voltage. We're talking around 20 kilovolts. As they fly down, they pass through a series of magnetic lenses. Notice how I said magnetic, not glass? Because electrons hold an electrical charge, we have to use strong electromagnetic fields to focus the beam into an incredibly fine pinpoint. Then, right before the beam hits the sample stage at the bottom, it zips through scanning coils. These coils basically deflect the beam back and forth in a super-fast grid pattern, scanning the surface exactly like the little electron spot in those heavy old-school cathode ray tube TVs.
Which brings us to Section 3. The interaction volume.
Okay, so our primary electron beam has been fired, it's focused, and it's rapidly scanning across our sample. But what actually happens at the exact nanosecond of impact? Well, when that primary beam bombards the sample stage, it's honestly a lot like a cue ball smashing into a rack of billiards. Bam! The collision instantly generates a bunch of different signals that go bouncing back up toward our detectors. The 3 big ones are secondary electrons, backscattered electrons, and X-rays. Secondary electrons, or SEs, are low-energy electrons getting knocked loose from just the very top surface layers. These are the guys that give us that gorgeous, detailed topography. Backscattered electrons, or BSEs, are primary electrons that literally bounce right off the atomic nuclei of the sample. They have way more energy, so they escape from much deeper down. And BSEs are super cool because heavier elements bounce back more electrons, letting us easily tell different materials apart just based on their atomic number. And finally, this intense collision also spits out X-rays, which give away the precise chemical composition.
Now, what's really interesting about this slide is the actual shape of the interaction zone. Do you see how it forms this distinct, almost teardrop shape just beneath the surface? When that incredibly focused beam hits the top, it doesn't just stop cold, it penetrates and spreads out deep inside the material.
You can clearly see how the low-energy secondary electrons, that dark brown strip at the top, only manage to escape from the ultra-shallow surface, maybe the top 100 nanometers. But those high-energy backscattered electrons in X-rays, they're blasting out from much deeper inside that wide teardrop. This actually means a wild thing for scientists. Sometimes the final resolution of the image is a bit poorer than the tiny size of the electron beam itself, just because that interaction volume spreading out inside the sample is so wide.
All right, let's pivot to section 4, prepping the perfect sample. So far, we've totally geeked out on the physics of the microscope itself, but there is a very delicate, honestly quite tedious procedural reality to all this. You literally cannot just toss a wet leaf or a bug into an SEM and hit the power button. Remember, the whole inside of this chamber operates in a massive high vacuum. If you put anything holding water into a high vacuum, that water will violently boil and completely obliterate the sample's microscopic structure in seconds. So, for biological or wet samples, we have to stick to a very strict scientific recipe. First up is fixation, where chemicals are used to freeze the biological structures perfectly in place. Next is dehydration, where we painstakingly swap the water in the cells for organic solvents, usually ethanol. Third is critical point drying. This is a crazy cool process that uses liquid carbon dioxide to gently remove those solvents so that no surface tension collapses the super delicate structures. And finally, step 4, sputter coating. Because the SEM relies on electrons to see, the sample absolutely, 100% must be electrically conductive. If it's not, the electrons will just pool up, charge the surface, and totally ruin the image.
So how exactly do you make a nonmetal, totally biological sample conductive? You use this neat little device called a sputter coater. Inside a tiny vacuum chamber, the device pumps in a bit of argon gas and cranks up an electric field. This creates positively charged argon ions. These heavy little ions get accelerated upward, violently slamming into a target block made of pure gold foil. The sheer force of the impact physically knocks gold atoms right off the target, and they drift down like this incredibly fine metallic snow. They settle over every single microscopic nook and cranny of the sample. It leaves behind this perfectly thin, highly conductive dusting of gold that lets the electrons flow smoothly once we start scanning.
Let's get to the fun part. Section 5, Seeing the Invisible.
And now for the ultimate payoff. After generating the beam, dialing in the lenses, managing the interaction volume, and painstakingly prepping the sample, what do we actually see? Well, look at this. And this brilliantly illustrates what we were talking about earlier. We have two side-by-side shots of microcrystalline cellulose, or MCC. Remember our definition of morphology? The shape and size of the individual particles? Just look at the extreme 3D detail going on here. On the left side, we can clearly see these long, distinct fibrous structures. But over on the right, the morphology is completely different. It's way more clumped up and irregular. The secondary electrons are just skimming along that gold-coated surface we made, firing back topographical data that lets our eyes perceive this immense depth and texture, even though these particles are almost unfathomably small.
Here's another totally spectacular example. Check out the extreme topography of these silver powders. Look at how the SEM captures the incredibly smooth, almost boulder-like curvature of these tiny particles. By studying images just like this, engineers and material scientists can instantly understand how these powders might pack together in a mold, how porous they are, or even how they might act in a volatile chemical reaction. This visual data ties perfectly back to our definition of topography, giving us this immediate, intuitive visual understanding of how the material is actually going to behave.
Finally, Section 6, SEM versus TEM.
As we start to wrap up this explainer, we really need to place the SEM in a broader context next to its sibling, the TEM, or Transmission Electron Microscope. While they both rely on electrons, their methods and their final results are super different. The SEM, like we've seen today, relies entirely on capturing scattered electrons that bounce off a sample. It is hands down unmatched for studying thick samples and checking out stunning 3D surface morphology. But the TEM, it's all about electron transmission. It literally shoots the electrons entirely through the sample. Because of this, TEM samples have to be sliced ultra thin. And while it only gives you a flat 2D image of the internal structure, rather than that cool 3D surface vibe, the TEM can actually achieve even higher atomic-level resolution.
Let's move to and see how this builds out visually. Notice the stark difference in how they're set up. Down at the bottom, in Figure B, you've got our newly familiar SEM setup. The beam is focused to a point, those scanning coils sweep it back and forth across a solid, chunky sample, and our detectors sit up top catching the bouncing secondary and backscattered electrons. But look at Figure A for the TEM. The electron beam stays really broad, it blasts straight through the incredibly thin sample right in the middle, and then it hits projector lenses that basically display the internal shadow of the material directly onto a fluorescent screen or a detector at the very bottom. One bounces off the surface for 3D texture, while the other shines right through to reveal the hidden internal structure.
From the initial firing of a tungsten filament, shooting down through magnetic lenses, diving into that teardrop interaction volume, and finally bouncing off a gold-sputtered surface straight into our detectors, the whole journey of an electron inside an SEM is just an absolute marvel of modern physics. It has completely transformed how we understand topography, morphology, and composition. But, as technology just keeps evolving, our resolution limits are shrinking further and further every day. Which leaves us with a pretty profound question. What other invisible worlds will we uncover as our tools push even further past the nanometer limit? Thank you so much for hanging out and joining me on this explainer. Keep wondering, keep exploring, and I'll see you next time.